To this point, we've introduced explicit methods for solving ordinary differential equations. Now, I want to show you an example of to motivate this next section of where we run into problems. And we run into problems with what's called stiff systems. Now, this is an example that they give in the book. This is a van der Pol oscillator, and this is a stiff system. And you can actually adjust the stiffness of this system with a parameter. But what happens is for a stiff system, the explicit methods that we've introduced already, these Runge-Kutta methods, all perform very, very, very poorly on stiff systems. And to give you an example of how poorly, I actually solved this. So this is the plotted solution of this ordinary differential equation, and I can show you. So here's the MATLAB code that I wrote to do it. The function is just dy dt equals y2. So this is a second order ordinary differential equation, but we can rewrite it as a first order, or as two first orders coupled. And so we do that. Dy dt1 is equal to y2, and dy dt2 is equal to mu times 1 minus y1 squared times y2 minus y1. Okay, what's the point? Well, and you adjust the stiffness by changing this parameter. The point is using ODE45, which is it's actually the Dorman-Prince method. It's similar to it's basically the same thing as it's similar to the Cash-Karp adaptive Runge-Kutta method, and so I told MATLAB to solve this problem using that method, and it took 230 seconds, almost 231 seconds to solve this problem, and that was sort of a long time to try to solve this relatively simple problem for a short period of time. Then I solved this problem again, and we'll get into the details of the other methods, but this is just to show you why they're useful. I solved this problem with an ODE solver that's designed to work with stiff systems, called ODE23S, and this solved the same problem in less than a third of a second. So this should give you some idea. Now, sure, just waiting a few minutes isn't that big of a problem big of a deal on this problem, but if you have a problem where you're solving possibly hundreds or thousands of variables, and you're waiting days or weeks or months to get a solution using a method like ODE45, that order of speed up is a very, very, very big deal, and it means a lot in terms of monetary resources. So the stiff is a stiff system is sort of a hard thing to pin down exactly, to pin down an exact definition. One of the things that it mentions in the book is for a stiff system, you have slowly changing solutions combined with rapidly changing components for stiff systems, and that's sort of not a very satisfactory answer, because you can find some counterintuitive examples where it doesn't quite behave the way you would want it to, but in any case, perhaps the best way, another way that you might define a stiff system is a system where the other methods, the explicit methods that we've introduced, fail miserably. I mean, they don't fail miserably. I mean, they can solve it, but they've got to use a step size that's so small in order to solve the system that they end up taking way, way longer than is feasible for the problem that we're interested in. And so that is the introduction to stiffness, and it brings up an issue. So why does this happen? Like, why does this happen with the explicit methods that we've talked about? And on page 753, I just encourage you to look over that, but I'm going to hit the high points of that discussion, and what they show is that at least for a specific problem, the exponential growth problem, which is basically the problem that I solved in a previous video, they show that the stability of the explicit methods, or at least of the Runge-Kutta methods, is dependent. So the stability depends on H. Okay, and this isn't just the stability for one little region. This is the stability for the whole problem. And so if you don't use a really small h for the whole problem, not just the part where it's rapidly changing, then you have some serious issues. And so the alternative is to use what's called predictor corrector methods, and we'll get into those a little bit more in a minute. But the big thing to know is that opposed to what happens, in contrast to what happens with the explicit Runge-Kutta methods, where the stability may depend on the step size, for the these other methods that we're going to talk about, these predictor corrector methods, they may be unconditionally stable. Okay, and that's really nice, because what that means is we don't have a stability that depends on the step size parameter, and so we can afford to use a larger step size in the regions where we see a small change, and a much smaller step size in the regions where there's a large change. So that again is stability and a stiff system. So this is what happens when you run into a stiff problem.